Hello everyone, I am Sadia and I'm here to present our work SWUNet, which is Swin Transformer Based Unit for Hyperspectral Super Resolution. A brief overview of the presentation. I have prepared a background, challenge and the solution to the challenge. The challenge in single image super resolution, motivation behind using our proposed method. Our method, the overview of our method, the input our method, and two succeeding blocks. The experiments conducted in our work, the results, and the qualitative results. We often ask ourselves, what is hyperspectral data and why do we need hyperspectral data? And why do we need its super resolution? Hyperspectral imaging data is an imaging technology for processing and collection across entire range of electromagnetic spectrum. Unlike humans, which can process and collect only across visible range. But we see that hyperspectral data is often compromised because of its limitations of incident energy. And this causes a trade-off between spatial and spectral resolution incurred. In this regard, we use a post-processing technique, a super resolution technique, which can infer high resolution image from low resolution image. And we divide hyperspectral images in two groups. One is fusion based and another is single image super resolution. In fusion based image super resolution technique, we use the help of extra information, which is the auxiliary information. But in single image super resolution, we do not have such advantage. And this method has also received less attention and there has been little advancement. So why are we doing single image super resolution? Because it's flexible and it's easily adaptable. So hence, using single image super resolution, we can build strong features which can help our low resolution turn to high resolution. And recently, Deep CNN have shown extraordinary capability of modeling this relationship. So the practical rationale is we have high resolution image and we have their corrupted version. We give it to DCNN method and we get the high resolution back. But challenge in single image super resolution are non-triviality to train a computationally effective and efficient network. Given to the popularity of RGB images, hyperspectral images are not as popular as their RGB counterparts. And because of that, there is limited number of training samples for hyperspectral images. And once we have those limited samples, the difference lies in the number of spectral bands and the imaging conditions. Say, for example, if we have a sensor, the sensor, two different cameras to capture the same scene, because of two imaging conditions and the different sensors used, we'll have limited data of the same scene. And also, one cannot ignore the spectral dimensionality of hyperspectral data, which is huge. Keeping these challenges in mind, we propose, we see quite motivation to work with spectral grouping mechanism because it exploits the correlation structure of hyperspectral images. And also, transformers have confirmed their superior performance on computer vision and NLP tasks. Recently, transformers have been used, a very famous transformer, Swin transformer, has been used for its generalizing capability for tasks such as image restoration, image classification, segmentation, and depth prediction. And thus we can say that it has shown a lot of promise as it integrates CNN and both transformers in one. So the method overview of our work is we have three components: initial grouping network, This causes band grouping based on spectral response function. We divide the bands, a particular set of bands, into three groups based or n groups based on the number of um, significant wavelengths there is to exploit. And then there are swing transformer blocks in contracting and expansive modules. We do not directly use swing transformer blocks, rather we use a residual swing transformer block. So RSTBs in SWONET are residual swing transformer blocks used in contracting and expansive modules. And at the end, we have a reconstruction block, which is an upsampling factor for a better interpolation technique. So the input to our work is based on three groups of bands rather than giving a full set. So our group of bands divide on the basis of spectral response function. On your left, we see a monochrome version of the camera coupled device, which disperses in the color version when the spectral response of the correlated bands is considered. We divide these bands are grouped on the basis of common spectral response function. So the bands having common correlation will be grouped under one significant wavelength, like as we saw in the previous slide. In our first group, we had 0 to 5 bands, and the significant band, the significant wavelength here, which is blue, thus groups five bands in it. And significantly, and accordingly, we have green band, and we have green wavelength and red wavelength. Green dealing with 6 to 15 number of bands, and the rest with red wavelength. So deep feature extraction happens in SWONET blocks. SWONET blocks consist of three RSTB modules and two patch merging modules. Instead of simple unit architectures in contracting path, we have replaced the blocks with residual swing transformer block. After residual swing transformer block, we change the feature maps engaging patch merge block. After patch merge block, we again use swing transformer block to give a specified F swing 2, which is the feature map from patch merge and swing RSTB. After this, we use the third unified block in the contracting path. As happens in unit, in the expansive path, which is this, we use the same RSTB blocks, but we unmerge these patches, which leads to the decrease in the number of feature maps um, at the end. And at the end of the SWONET, we have FDF, which is deep feature map from SWONET block. The final restoration block is pixel shuffle. We have replaced a simple bicubic filter using a pixel shuffle. This imaging, this upsampling is better than a normal bicubic filter because it takes into consideration t-square channels and changes them into 1 over t stride in the high resolution image. So that's pixel shuffle. Therefore, at the end, we also use one interpolation technique to just get the low-level features into the existence. So these are the experiments, implementation, and training. We use two data sets, CAVE and entire 2022. The learning rate is kept same as Swin Transformer. We are training entire 2022 for 100 epochs and CAVE for 400 epochs. We conduct experiments on an upsample factor of 4 with a batch size of 32. The experiments are conducted on single NVIDIA A6000. We have tested entire 2022 on 50 challenge images and CAVE dataset on 5 images. The results obtained on entire 2022 and CAVE dataset with our proposed methods are shown in our table. We understand that with a upscale factor of 4, we do not achieve better results than SSPR, and this work is a work in progress also. We are trying to get better, but we have surpassed every other method in CAVE dataset with 3 dBs, approximately 3 dBs in everything. These are our qualitative results, and these figures show the error maps of the methods. We have MCNet, HSISR, SSPSR. These are three convolutional neural network based methods. DS-trans is a transformer based method. So in conclusion, we propose a unified swing transformer based unit adaptation. It is one of the earliest attempts to leverage a transformer in unit-based architecture. We demonstrate it by achieving better quality results in reconstruction from using low-resolution HSI. These are the references that I've used in our work. Thank you for listening.